What's good, guys? My name is Divi. Today we're going to be talking about power. So power is the rate at which work gets done, and it is the amount of work over the amount of time in this symbol. However, since it is a rate, we can represent it as a derivative in calculus rather than algebra. It's also noticed as this, which is just the instantaneous change of wattage or work in terms of time. The really confusing part is watts and work have similar symbols, just work is italicized and watts is not, but honestly, I think it's kind of hard. So whenever I'm gonna write watt, I'm gonna probably write out the whole word, except when it's like units, right? 1 watt is 1 joule per second. If you think about that, it makes sense, because work is joules, time is seconds. Okay, and then this is just talking about some history. If the equation for work done by constant force is namely this, then we can insert it for the power, where R is displacement. The equation becomes this. And then we can also write power, because this is just rate, the change in x, right? We can write this into F times velocity equals power. Okay, by contrast, this is another fun fact, yada yada yada. Okay, a mover pushes a large crate, mass M, fit 75 kilograms from inside the truck to the back end, distance of 6 meters, by exerting a steady push of 300 newtons. If he moves the crate distance in 20 seconds, what is the power output during this time? So remember, our equation for power is the amount of work done over the amount of time. We know the work is equal to force times the distance. If we put terms of this, our force diagram, we know that the force applied is here. We're assuming that force of friction is 0 just because it's just not noted anywhere. And let's assume that the force applied is in the horizontal direction, because they don't also give us an angle. Okay, so we know S is equal to 6 meters. We know T is equal to 20 seconds. And force applied is equal to 200 newtons. They gave us that. So in terms of work, we can write our force. Sum of forces equals mass times acceleration. And since it's a steady push, acceleration equals 0. So actually mass in this case doesn't matter. But initial is not. So 300 newtons. So this is a positive direction. We can get acceleration, which we don't need to solve in this case, but if we needed to, then we could solve it that way. But using our equation we do have here, it's 300, correct, not 200. So we can solve this to get 1800 over 20 seconds equals 90 watts. This is watts, not the thing. Same thing we got here. Okay. Now I think the next one will be doing somewhere in acceleration and velocity. Okay, what must be the power output of a rocket engine which moves 1,000 kilograms at a constant speed of 8 meters per second? In 2 meters per second is the rate at which it moves. 1,000 kg. And since it's a rocket, let's assume it's actually going in the upward direction. 1,000 kg, 8 meters per second. Let's assume the positive direction is accelerating direction. We also have mg over here. So sum of forces equals in the y direction, which is the only direction in this case, because sum of force in x direction just equals 0, assumed. Mass times acceleration, which equals to negative force of grav plus force applied. And we know that m over here is 1,000. We know mg is equal to this. And we're looking for power. We know power is equal to force times velocity. Simply, since we know that this is 0, since acceleration is 0, we can simplify the sides mg equals fa. Thus, doing this, force applied will equal to 8, or I guess 10,000 newtons. And using this fact and multiplying by 8 meters per second, we can get nanometers joules per second, nanometers per second. What am I saying? Newton meters per second, which is equals to joules per second, which is thus equal to 80,000 watts, or 8 kilowatts. Okay, here, these are some practice questions. I don't know why it's sliding weird, so I'm going to reopen the page. Just some free response questions we can do later. And just like that, let's go over the summary real quick. Potential energy can be given in terms of U of x, then F force is always equal to the negative of the rate of change of potential energy, because since they're inverse relationship, when one goes down, one other goes up. If the potential equals this, then the force is equal to this, and it's at an equilibrium point. Because when we think about this relationship in specific, the force is the rate of change. This is not talking in terms of potential. When the rate of change of potential energy is 0, that means it is at a stable point. This means that either there's no potential energy, or all potential energy is 0 and everything is in kinetic energy. Stable equilibrium occurs when the force returns the object back to equilibrium point after it's disturbed. And unstable equilibrium forces the object to move away from the equilibrium after it's disturbed. Thinking it in terms of motion, whenever it's looking like this is unstable. Whenever it's other way around like this, it is stable. And when we think of a spring and how this works, think about the regular inch of a spring being stable, and this is the 0 line. If we're above this, since it will be moving in the negative direction and towards the 0 line right here, it will actually be more potential energy going into the negative direction, so there would be a positive force. That makes sense, and we can redo this information also over here. Just confirm. Since Ux is decreasing at points A, B, assume that since this is high potential energy because the string is really short, when it increases, it will be accelerating in the positive direction. Because think about the spring is expanding, rate of change of this Ux is decreasing, thus this would be stable. Okay, now since the spring is going the other way, if it's super long and then it's going back towards the equilibrium, or even if it's long but less than the equilibrium is going still this way, on both sides, we have to call this unstable. However, if we were on this side over here, it would go this way. And if we were on this side over here, it would go this way. Because these are different directions. Or just looking at the slope, right? At both of these points, the change in x, since they go through and are negative in the first half and positive in the other half, they're good. But since this is positive in the right, but the negative in the left, it is unstable. That makes sense. The power is done as this, which is all equal to this. Okay, let's start with linear systems of particles and linear momentum in the next one. Appreciate guys. Peace.